just for your information.
Yeah.
ठीक है. ठीक है. मेरा लैपटॉप क्रैश हो सकता है, अगर हुआ तो कुछ करेंगे. लेट्स.
ठीक है.
ठीक है. तो ठीक है, आज देखो, okay, so today I'll just talk about like history of non-Euclidean geometry and some, let's say, philosophy about it. So okay, so let's start with what is Euclidean geometry. So so Euclid, when he wrote his book, he gave 5 postulates which he thought characterizes Euclidean geometry. So first one was so first was he said if you have any 2 points in your plane.
अच्छा, rest of you, can you mute yourselves? Like थोड़ा background noise आ रहा है random.
No, it's fine.
एक मिनट, चैट में कुछ आया क्या? Yeah, ठीक है. Yeah, I was saying, so if you have any 2 points, you can join them by a straight line. ठीक है. Obvious thing you would want. Also, this is also 2-dimensional Euclidean geometry. Let's not go higher dimensions. So this might be vague right now, what is 2 dimensions and what, but it'll get clearer later. So the second postulate was this. So if you have any line segment given to you, you can extend it on both sides indefinitely. That was the second postulate. The third one is so the next one was if you have a line segment, you can draw a circle with one of the endpoints of the segment as center and the whole segment as radius. Okay. So, and fourth one is so fourth one is all right angles are congruent. So what does this mean? This why do we actually need this? So we actually want straight lines to be like this, right? have same angles on both sides. You don't want straight lines to be like this, where these two angles are same, but they are not the same as 90 degree. So that is what this this postulate is capturing. Okay. So the fifth one is slightly problematic because it's big. Okay, so fifth postulate is if you have um, two lines which intersect at third like this. Suppose you have two lines. Then you have a third line. And if it so happens that these two angles together sum up to less than two right angles, then this postulate says these two lines extended far enough on this side meet at some point. Okay, so so these were 5 postulates Euclid gave 2000 years ago, more than 2000 years ago. So after that, mathematicians for some reason thought that postulates 1 to 4 writing. Okay, my laptop has crashed, so give me 2 minutes to restart. Any questions till now, please?
Yeah, laptop नया है क्या?
हाँ, laptop नया है, but for some reason combination of Zoom and anything else crashes it.
अच्छा.
So what sort of new laptop is this then? Yeah.
Yeah, I don't.
He got scammed.
Again.
Again, oh shit. रुको.
So wait, the screen we are seeing, is that from your laptop right now or your phone?
That was my laptop. I don't know why it is still there.
Yeah. Okay, fine.
Yeah.
It's finally closed.
Like, I'll just use the whiteboard. Okay. So I was thinking for some reason mathematicians thought for that postulates 1 to 4. 1 to 4. they actually imply the fifth postulate. So they were trying to say that for some reason, the first four kind of encompass the fifth one as well. So fifth one, as I stated it, it was in a weird way. So what it actually means is it is actually the parallel postulate, which is so what it says is if you have a given line and a point not on that line, so there exists a unique straight line passing through this point. So this line is unique and this is also parallel to this line. Okay. This postulate is also same as saying if two lines are parallel, the angle here both are, sorry, not both are, let's say this one and that one and this one, they are equal, like the interior angle or transversal some property there. Okay, so all these are equal. This is also same as saying distance here and distance here is the same. Okay, so so for like 2000 years people thought that this is actually you could actually deduce it from the first four. It was only in around say 1830, like Gauss, Bolyai and Lobachevsky made some, they like discovered a non-Euclidean geometry which was actually consistent. So what is non-Euclidean geometry? So this is a model which satisfies postulates 1 to 4. So it satisfies 1 to 4, but not 5. What does it mean? If you have a line and a point not on this line, either there is no line parallel to this line passing through the point, or there are infinitely many, like infinitely many which go like this. So this, of course, is not intuitive.
Wait, why does it have to be infinitely many if not
It
none?
could be. It doesn't have to be. It could be.
Like, no. I mean, if it's not no lines, like, can it not be a finite number of lines?
Oh yeah, sure. There can be finitely many as well.
Oh, okay.
I'm just saying how it could fail. What are the ways?
Oh,
Right.
okay.
Yeah, it could be finitely many as well. Like there could be 3, 4. Okay, so that is how the fifth postulate can fail. But so their point is like what Gauss and Lobachevsky tried to say was there is a consistent system where 1 to 4 is satisfied, fifth is not satisfied, but they together are like fine. Okay. So yeah, so when Lobachevsky actually published his work on this, it was not taken very well. He was fired from his institute for some time. Yeah, it took like 30 years after his publication, like after some of Gauss's private papers were released, only then people started like taking this seriously and taking, like, this got popularity after that. Okay, so how did they, so what is an example of this non-Euclidean geometry example? So first example, or I will just give an example of hyperbolic geometry directly. So you look at the upper half space, just stop. So in this space, all lines perpendicular to my real line here, all lines perpendicular like this, I will call them to be lines. So lines are okay, all vertical lines in, okay, not C, upper half.
Karthik, before you move ahead, what do you mean by consistent system? Like you said, it satisfies 1 to 4.
So
And but
consistent means it's like there are no contradictions in between themselves. Like like assuming 1 to 4 and not assuming 5 might have been contradictory, right? If like 1 to 4 implied 5 and
okay,
I say assume 1 to 4 and not 5, that would be contradictory, right?
okay, okay.
Yeah.
But the definitions of lines will change
Yes,
in the
exactly.
okay.
Exactly. So our definition of lines will be different now. So all vertical lines in the upper half space, they will be lines. That's quote unquote lines. And also all circles, semicircles like this, like semicircles with center on the real line. So all okay. So this is our jump. This is our space for now. We have redefined lines. So I will not tell you why this satisfies 1 to 4, but I will only show you why it does not satisfy the last one. So yeah. So suppose you have this line. Oops. Suppose you have this yellow line and this point not on it. You can find so basically for every point in between here as well, you can find a semicircle going through this point. So what happened here is you have a line and a point not on it, and you have infinitely many lines going through this point, which do not intersect our line here. So in my new system now, parallel also will mean not intersecting. Okay. So okay, this was in the language of Euclid, which is not quite not the language we currently use. So translating this to what we do it now, let's try to say all this in a like very slick and compact way by doing this. So what are the things we need? So since we are trying to do two-dimensional geometry, let us ask it to be a surface. So the smooth surface, right? Smooth, because why not? We also need a notion of distances so that we can measure radius and draw circles, which is a metric. Okay. we also need a way to measure angles. Okay. Then we also need orientation. So that we can talk about sides. So these are the things we need right now. So this can be done by saying, okay, I will start by X be a smooth surface. So here I need to measure angles, right? Let's start with measuring angle. But I haven't told what straight
Just a
lines
question.
are. Or, yeah.
Like, how does a metric come in? Like in, say, in the previous postulates, like there was nothing about distances, right? Or was it?
Okay, where did it go? Oh, it was in the other screen. Okay.
Yeah, just
Yeah, metric is not really necessary, but yeah, it'll just be a consequence of what I do right now. But to do geometry, you also like need distances, right?
yeah, okay, fine.
So at some point you will need distances, but this is not the like standard Euclid's geometry, but at some point you might need it.
Okay.
Okay, for
Consequently, it will just come up.
for
Yeah.
clarification, is image z is greater than or equal to 0 or just greater than 0?
Greater than 0. The
Okay,
real
but-
line is not included.
Okay, real is okay.
Okay. So how can I measure angles, or whose angles do I want to measure here? Let's do like the most general way by saying, okay, I just want to measure angles of curves. Like I have a curve here and a curve here intersecting. I want to measure angle between them. What would I do? I would take tangent vectors here. I take tangent vectors to this one, tangent vectors to this one, then try to measure an angle, right? So we are trying to basically measure angles in the tangent space of this point. So angle will also be like this, right? Cos theta will be inner product by yeah, I hope I'm right on this. Yeah, whatever, it will be something like this, right? So basically to get an angle, we need an inner product and a norm. But actually just an inner product will do because that will give a norm. So basically what we want is you want a positive definite inner product. Okay, so you want a positive definite inner product on each tangent space. And to make sure it's like neighboring tangent spaces are comparable, I will also ask it to be smoothly varying, like in some sense. So here in my definition, I will say, let X be a smooth surface with uh, okay. So yeah, so now, so this satisfies everything, right? Oh, I have to add oriented. Yeah, so this satisfies all the things I need. So It is a smooth surface. Smooth surface. It has a way to measure angle. It has orientation. It also has a metric implicitly defined, but might not be direct from the definition, but it has one implicitly there. So this is also so this is what is called a Riemannian manifold, and most of what we do will be in the Riemannian manifold setting, and this is sort of motivation for why we are doing it here. So in these Riemannian manifolds, my lines, my quote-unquote lines, they will be geodesics. Geodesics are, let's say, let me say length minimizing. Okay, they're not exactly these, but you can think of them as length minimizing curves for now. Then again, parallel means okay. So parallel will be not intersecting. So to get my original picture here, to get this kind of geometry and where like these lines are geodesics, I will be using this metric. So it's not. So this will be my metric. So dx square plus dy square just on its own. This is the regular Riemannian metric we get on R2. I'm just like scaling at each point by a scalar multiple there, which means like angle you measure in this new geometry and the ones you measure in R2, they will be actually the same, but lengths of course will be different. Okay. So okay, so I will stop here today. Maybe we can start with like proper calculations and other stuff next time onwards. Any questions?
नहीं सही है.
सही है, ठीक है. चलो, wait, how do I stop?
Next day 9 p.m. क्या?
Next
So
time.
I just had one
Yeah,
question. So your metric is by y or y squared?
I think y is okay.
I don't remember. That's why.
Oh no. Yeah, it's TSS square. So
Yeah, I think it should be y squared. Yeah.
yeah, it should be y square.
I'm not sure.
Yeah, I also. I mean,
will-
I only know what I know.
Let me check,
Also,
let
in
me
the
check.
inner product, it's 1 by y squared. But I mean, I forget what happens. And
yeah,
I mean, I
even
don't
I'm
remember.
confused. Yeah.
Yeah.
Yeah, I'll just check it and make sure I'm correct next time. Okay.
Yeah.
Yeah, it's 1 by y square. DSS square equals to dx square plus dy square by y square.
Okay, I think I was thinking about ds.
Yeah.
Okay.